It's a very technical term.
Yes. It's like what do you call it? What's the other term? What do you call it? The big grip. The grip. I forget.
Stop.
Do it. What's the?
You started. We're recording.
Yeah.
We're live.
Oh.
Okay. So thanks to these two being douchebags to each other on this on the 1-year anniversary of Nerd Salon.
Yeah.
It was more like a 1-year anniversary of the Sci Tech page, but kind of the same thing.
I think we should be banging on our shields.
On interstellar travel. For centuries, human beings have been reaching for the stars.
Get to the presentations!
I want a clean fight.
Yeah,
no biting, no scratching.
So anyway,
lots of
keeping on the whole 2001 Space Odyssey part, these two fellows are going to present two different spaceship designs for interstellar travel. And you, the audience, shall be judging and watching and enjoying and obviously learning.
Potentially, you know. Okay.
Or heckling maybe.
Yeah. So the criteria are basically no God-winning, no logical fallacies, no name calling, no lusted trolling, and at the end of it, the audience will be voting on which designs are best based on 3 criteria. 1 is on the speed it takes to get to its destination. 2 is on how realistic it is, or how within the realm of possibility it is, and the tiebreaker of the 2 will be the creativity, how creative it is. So you better listen, give it a vote with your hearts and not your minds.
I thought we were voting for mind. That's bullshit.
Thank you. A wonderful presenter.
Oh, wait again for a second. Go on.
Don't give up your day job.
Wait for a second. Wait again. Wait.
Oh, where? I thought you said wait.
Alright.
This shall not go on your profile picture.
No. But it can go on my profile picture.
It goes on a very separate profile picture.
I am Akesh. No, I am Akesh. No, I am Akesh.
I am Akesh. Yeah, I think
When we get to the last slide, you let me know and I'll get out and you do your thing.
Who's doing the intro?
Well, you put the slides together, so maybe you should start with the intro and I can chime in where I feel like chiming in.
Right.
That's it.
So this is not my presentation, but this is the common introduction made by both of us about the challenges of interstellar travel. And so this is the common objective that both of us are trying to reach, is to reach the star Alpha Centauri, which is 4.3 light years away. Oh, let's actually
let's show you. Keep some
let's
visual here.
Let's stick to this. And
Alpha Centauri is the closest star to us. It's not one star, it's a system of stars, 3 stars actually. One's a red dwarf star, they're kind of crappy, we don't really worry about them right now. That's the one that's closest to us. And the other 2 are a double star system. One is a class G star, G2, just like ours. And the other is we call it class K star. So that's so it's an orange star, and they orbit each other. And that's Proxima Centauri right there. See how it's redder and smaller? That's 4.26 light years from us. The main system is over here, and it's 2 stars. You'll start seeing that's putting in a moment now. So both these stars may have planets that are Earth-like. They're still trying to figure that out. Part of the problem is they orbit each other, so it's hard to tell, because the way we do astronomy to spot planets that are around stars involves involves one star being still relative to the planet. So, but we think it has worlds.
so, right.
Probably like ours.
So, a little bit about the challenges of interstellar travel. Right, so types of missions. Ideally, you can do a flyby.
Who knows what a flyby is?
It's like a drive-by.
You explain it.
So the thing about space is you can't shut off the engines and suddenly come to a stop. You have to brake. If you don't brake, you're just going to overshoot your destination and keep on going. So that's a flyby.
Flybys require less energy and fuel, so they're cheaper. A lot of what we know in space science about our outer system, about Saturn and so on, is from the Pioneer missions and the Voyager missions, which are flybys. And the Voyager is the fastest vessel we've ever built. And they went skirting right past these planets and took pictures as they went. And for like 20, 30 years, that's all we've really known about some of these places based on those flybys.
So the next thing is a probe, which is you brake at your destination, Alpha Centauri, go into orbit, but it's still unmanned. Next thing is explorers. You send human beings there, and hopefully safely bring them back. Fourth option is you send colonists. This might take centuries to get there. There's no return, and they're just going to establish a colony there.
We've set some dates here to try and make it a little interesting. We want to see how we want to come up with a system that would have human explorers go on a return mission for 2100 and colonists there by 2200. That was our challenge, working with those bounds. That's actually very little time.
Right. Problems of interstellar travel are these. Now, okay, so on Earth, you have stuff to push against, right? Vehicles push against the road, ships push against water, jets push against the air. But in space, you don't have anything to push against. So the stuff you push against, you have to carry with you. This is what you call the propellant. You have to push something out the back of the spaceship in order for you to go forward. But if you're carrying that, you have to carry more propellant in order to propel the propellant. So it becomes an exponential problem.
To give you a quick thought experiment, right? Let's say you want to drive to Jaffna. Alright, how many times do you get to stop for gas to drive to Jaffna?
How many times am I going to?
Would you have to stop for gas?
Maybe once up and once down, or twice.
Okay, so 2 tanks, right?
Yeah.
Now, how many liters are in your tank, you know?
Ooh, I can't remember. Sorry.
10, 20?
Probably more. Probably
Say 30?
40, 30, 40,
45.
50 liters, right?
Okay. Now let's say you fill up your tank, you say you fill up your tank to get to Jaffna, right? You have 50 liters. But you're not going to tank up when you go there. You have to have your fuel with you. So you take another 50 liters with you. Let's say you can put in the back. It's just 50 liters, right? Very manageable. You can carry all your fuel with one stop, right? Now let's say you want to drive, things are good. Modi says you're okay with this, we're going to go, and they build a causeway. You want to drive to Delhi. How many tanks are we talking now? You're probably going to stop maybe what? 4 times? 5 times?
A lot more. A lot
more.
more. A lot more. Maybe like, yeah, maybe
10? Yeah,
maybe 10. Yeah.
Let's say 10, right? So it's 500 liters. What if you're going to carry all 500 liters with you because nowhere will give you petrol? There's nowhere to stop to get petrol. Suddenly you may have difficulty carrying that in your car. Now let's say you're driving across Asia from Sri Lanka. You want to go to Istanbul, all the way right to the shore, and outside the other side is Greece, and you'll cross right to Asia. How much fuel are you carrying now? Suddenly, okay, let's say we go away from the car's not pulling a trailer. Let's say you got a great big, truck, or an LPG carrier, right? Will that have enough fuel to make it all the way and back? And after a while, and let's say it is enough. Let's say one LPG carrier can get itself all the way to Istanbul if it gasses itself as it goes, right? It will need that same amount of fuel to come back from Istanbul. If it carries it with it on its way, it's too much weight. It simply couldn't do it. And this is a problem with space travel because we have to carry enough propellant for 4.5 light years just to get to the nearest star.
Yeah. And just to give you a scale of how far away the nearest star is, let's assume Earth is like marble here. Mars is like marble here. Can anybody guess where Alpha Centauri would be? Okay, some people know. Alpha Centauri would be somewhere in...
We have a guess,
Yes.
Yeah, Navin.
That's one very funny. It'll be somewhere in Tirulapana or Nugegura. That's where it will be.
Hope so too.
So it's like this, and those are the interstellar distances. So yes, that's the problem. We're good. And we start with
On about now.
so
Now the duel begins.
now the duel begins based on a coin toss, and I have been fortunate to go first.
Oh shit, the title.
Can I stand here? Or
Yeah, go ahead.
Can everybody see this? Or shall I just...
Stand wherever you need to, we'll move around.
Yeah, we'll move for you.
Oh, no. Giving anything is...
All the answers are there, Navin. All the answers.
Right. Okay. My concept is called Project Bifrost, and as I go through the presentation, you will realize why I am calling it that. And as we discussed before, you have 4.3 light years to cover. Sun is here. Alpha Centauri is a binary system. Orbiting these two stars are a number of planets, and we have reasonable reasons to believe that there are at least 2 planets within the habitable zone of these stars. So the concept I am presenting is a ship to get there at half the speed of light, 0.5 c. And accounted for acceleration, it's going to take approximately 10 years to get there. And it's a very minimal, lightweight ship carrying just 3 people, which is not a big problem. As I'll explain later, they'll be asleep most of the way. Okay. So before I get into my concept, I want to talk a little bit about how we came to this entire topic, which is Project Daedalus. This is the last serious professional attempt to design a ship that can go to a nearby star, unlike amateurs like ourselves. This is a ship designed by the British Interplanetary Society. They came up with this thing. Just to give you a idea about the size of this thing, this is as tall as the Empire State Building, weighs 50,000 pounds. Maximum speed it can reach is 12% of the speed of light. Like Navin explained, this is all that fuel and propellant you have to carry with you. What's worse, okay, it will take about 40 to 45 years to get to the destination. It's unmanned and it has no brakes. And at 12.5% of the speed of light, if it finds a planet, it's going to whiz by it in a matter of hours. So not very nice. There's a newer incarnation of this thing called Icarus. It can go up to 30% of the speed of light, but it's 10 times heavier and still unmanned.
And still a flyby?
No, it will go into orbit, but unmanned. So that 10 times the weight is just to brake, and it's not coming back.
Yeah.
Does the duration reduce with the increasing speed?
Yes, so if it's 12% to 30%, it will probably be half the time.
So sorry, what does it actually do once it gets into orbit? It just stabilizes and drops pods into the atmosphere?
Drops probes and it will transmit back the data.
Okay.
Sorry, yeah, questions after. No,
Right. So, okay. Now, because of this problem with propellant, there's a certain concept that all amateur interstellar ship designers go to. This is the go-to solution for the problem of propellant. It is called the Bussard ramjet. How many of you have heard of the Bussard ramjet? I know there's one person who, yeah, a bunch of people know this. Here's how it works. It works on the same principle as a regular jet. What a regular jet does is, it sucks in air that's already in the atmosphere, heats it so that it pushes out the other side. So all it needs to carry with it is the energy to heat it up. It doesn't need to carry propellant. Unfortunately, in space, there's no air, but we have something else, something called the interstellar medium. It's extremely thin, something like even if you take an amount of space the size of this entire room, you won't even get enough atoms to make up a speck of dust. That's how thin it is. But the person called Bussard came up with an idea. If you have a large enough scoop, and if you move fast enough through the interstellar medium, you can grab enough matter to use as propellant. So this is the front of the ship. Push it out the other end. So that way you need to carry only the energy. You don't need to carry the propellant. Now the interesting thing is, this is not the scoop. This is just a small part of the scoop. The actual scoop is a magnetic field. it will stretch out like that, something like 100 kilometers, hundreds of thousands of kilometers. That's the kind of area that you need to grab enough atoms just to accelerate the ship. So there are two problems in this. First problem is, after Bassard, recently people have found out that interstellar medium is not as dense as we thought. So this won't be able to accelerate as fast as Bassard originally calculated. The second problem is, if it's like a giant scoop, this is like trying to accelerate with a parachute. Yeah. So there's a drag. And some people have calculated, if you have a giant collection field, you will probably be able to accelerate to about 20% of the speed of light, and that's it. And some people have contested this. So anybody who's trying to use a plain old Bassard ramjet is just deluding themselves. This is not going to work. But as you know, I have settled on a Bassard ramjet. How am I going to solve this? I'm going to solve this using two parts. First part is the easier part. The first part is the ship, right? And anybody who has read Stephen King would know why I'm calling this the Langolier, right? Okay.
Why is he calling the Langolier?
And here's a jumbo jet for size comparison. Yeah. And this moves in this direction. Okay. This is spool. So just like the other thing, there's a giant magnetic field. It catches as much interstellar medium as possible. And it's constructed of a material that we have spoken about today. This is one of the technical advances you are going to need in order to build this, graphene, just to keep the weight down. This is an extremely lightweight ship. 65 pounds is extremely lightweight, just to give you an idea about how lightweight it is. The space shuttle, the net weight is about 80 to 100 tons. So it's very small. It doesn't carry a lot of propellant with it, just enough for you to get the initial takeoff speed, so you can start collecting things from the interstellar medium, right? And the engine is a fusion engine, works on deuterium. The fact that you're traveling so fast causes the deuterium to smash against each other and ignite. That's what we call inertial fusion. And while it's not traveling fast, you still need energy, the power plant. That could either be a laser fusion reactor or a regular fission reactor, depending on what is available at the time of launch, what kind of technology is available. And the cargo, the habitat, you're going to need a lander, and you're going to need instruments. Those are going to fit into the outer surfaces of these petals. Yeah? And these things are going to contain the superconducting coils, which is going to generate the Bassard collector field. Fuel is deuterium, extremely common on Earth. Propellant is externally scooped, but I'm going to explain this later, the whole problems I told you about, how I'm going to solve this in the second part. 3 crew members, they are going to be asleep for the 10-year trip. And it's going to generate 450,000 newtons of thrust. Forget about the cost, because I've allocated a $1 trillion budget for this. And this is the small part. The rest of it is going to go to part 2. So some of the design decisions. Petals are going to contain the Bassard collector coil. Also, it's going to act as a debris shield, because when you're traveling fast, if there are tiny specks of dust, if it runs into you, it's going to blow a hole. Usually Bassard collectors have like a shield in front. It's just like a jumbo jet, it's going to hold some of the propellant tanks in there. And if you want, there's a certain amount of steering you can do using varying the magnetic field, slight amount of steering. And here's how I'm going to deal with the drag problem. The field this is going to generate is smaller, and in the next slide I'll explain why it can be smaller. This also helps collision avoidance. If you have medium-sized objects in your way, you can make a course correction. If it's a small object, you have these little gaps in your cone. You can shut down the electric field for a short time to allow these things to pass through. If it's tiny, it will ricochet off these things and go out here. So unlike the other designs, you don't have like a head-on collision of debris. It's on the side. It's going to ricochet off. And the habitat is tiny. Those 3 astronauts are going to be in an area which is no bigger than this room and that kitchen compartment. We don't have hibernation yet, but since this is going to be a 10-year trip and a 10-year trip back, we can get away with something like an induced coma, provided that the astronauts are okay with losing 20 years of their biological lifespan. Right. How am I going to solve the problem of not having enough matter in the interstellar medium? It's by preceding a path. Just imagine there's a path like this. If you don't have enough matter in your interstellar medium, you create a corridor with enough matter in it. Right? Imagine if you launch your fuel, your propellant out into space ahead of your ship, and you disperse it out there. All of a sudden, you have a corridor made out of not just hydrogen or anything else. You can have the exact fuel mixture you want, deuterium. You send it out there, later you send the ship. So this is an artist impression, but can you spot the ship? Right there. It's running with engines hot. This will most likely be kilometers wide. This is just an artist impression. So that's the idea. We are basically going to create a runway paved with fuel for this thing to travel along. So the next question, the big part of this project is how are we going to get the fuel there? That's the hard part. This is how. This is why I call this Bifrost. You know that in Norse mythology, Bifrost is a rainbow colored bridge that bridges Asgard and Midgard, which is Earth, right? So that's why I call that. It's a corridor or a runway that allows you to accelerate a ship. What you're going to do is, we are going to have a circular mass driver. And remember that when you accelerate something in a circle close to the speed of light, you're going to generate massive amounts of centripetal force. You need something strong enough to hold the whole thing together. And if in the circle you take tighter circles, the harder the material is going to be. So in that case, this thing is going to be huge. I calculated it needs to be at least 3,000 kilometers. It's going to be constructed out of graphene, and the graphene needs to be at least 1 meter thick. Right?
So multiple layers. Sorry.
Huh?
Multiple layers.
Yeah. So what it's going to do is, this is about 100 times bigger than the Large Hadron Collider, but based on the same technology. Superconducting magnetic track, accelerate around it. It's like a slingshot and send it up. What it does is, it has capsules of cargo which is about the weight of a normal human being. Most of it is either fuel or cargo. Accelerate to about 25% of the speed of light. And if it's just fuel, when it comes to the area where you want it to be, you can just let it disperse into space. But if it's cargo that needs to go into the destination before you get there, you need the way to brake. That's where something called a mag sail comes in. Remember I told you that a buzzard collector is like a giant parachute? You can use it to your advantage. You can deploy it and use it as a parachute, slow down near your destination. So I've allocated 20 kilograms for that. These are tiny little pellets. You can fire these things, accelerate and fire these things once it takes 15 minutes to accelerate this to 25% of the speed of light. This is huge. Remember Enceladus, that moon that we talked about on the forum? It can hula hoop through this. That's how big this thing is. Right? And one of the things I thought about funding this is going to be extremely expensive. Funding is to double this as asteroid defense. Because one of these things, 70 kilograms traveling at 25% of the speed of light, is going to have the same energy as thousands of Hiroshima bombs. It in fact has almost the same energy as the largest nuclear weapon ever tested on Earth, called the Tsar bomb, done by the Soviet Union. Something like 50 megatons. So imagine firing one of these at an oncoming asteroid at every 15 minutes. And that's enough to get it funded. It's a multi-purpose thing. And this is why I have placed it at the location I placed it is Lagrangian point L3. This is the point which is on the opposite side of the Earth from the Sun, because you will never be able to directly target Earth using this. Yeah. So this thing will have to start launching fuel ahead of time. And this is the schedule. First of all, you need to start pre-launching fuel about 5 years before the launch. And the runway you are going to need to accelerate to 50% of the speed of light, I calculate to be about 1/5 of a light year. And you accelerate for about 9 months. After that, you shut down the engines, coast for 8 years, cover almost 4 light years. On the destination end, by that time, the destination end runway has to be ready for you to decelerate. Fuel has to be there. You do the same thing. Arrive about 10 years after launch. And you explore for about, wake up, astronauts wake up, explore about few months, go back to sleep, wait for the outgoing runway to be ready again, because it's continually launching. The mass driver is continually launching fuel. Accelerate again, do the same thing in reverse, come back, if all goes well, back in 20 years. That is the schedule. So,
That's the right spirit for this. Totally.
Right. So, the most super optimistic scenario is this. Let's assume that they have the James Webb Space Telescope up and running by 2020, and they find that there's an oxygen atmosphere in. This is the most preferred candidate for an Earth-like planet, the planet called Alpha Centauri b. If they find that, maybe there will be a mad rush to get a probe or a mission there, right? Let's say construction takes 10 years, that's extremely optimistic again. Launch in 2031. They get there 10 years later, 2040, and because of the speed of light limitation, their first signals are going to come to us around 2045. So it will be 2045 when we will see the first images of them landing on a planet. So I will be about 65 years old, some of you will be about 55 years old when you see the first images of a human being landing on an alien planet. Questions?
That was fucking brilliant.
That's brilliant. Well done.
So it's just to observe and report, yeah? That's the mission, observe and report.
Observe, report, and safely return.
Yeah.
Safely return.
2 questions. Sorry, go ahead.
What about life support?
They are going to be asleep for most of the trip. They're just going to have minimal life support. So just enough for 2 months, because that's the only time outgoing trip, incoming trip, they're going to be asleep. Just for the period they are exploring, they're going to be awake. And if there's enough supplies that can withstand the mass driver's acceleration, robust things, you can send it out. The whole concept of this thing is only the fragile cargo you send the slow way. Human beings, if you accelerate using mass driver, they are going to be pancakes by the time they get there. Right? So those guys, the delicate instrument, you send them the slow way. Everything else, fuel, supplies, you just launch using the mass driver.
Sorry, 2 questions just on a question on in terms of how is this working. So once you present and you present, do you kind of rebut each other a bit? Is it like
Fox News? But if you want that, we'll
no, because that's like kind of Westminster rules where you can't bring new content, but you can, if you want to poke holes in each other. Do we do that, or how do you want to do it?
If you have time, we'll do it.
Like 2 minutes.